we're going to start with Sherelle Liu from Columbia University, soft place in my heart because I went to Columbia, so we got to meet backstage. She's going to be talking about Hammock Tower, climate resilient architecture for a plus 4 degrees Celsius future, leveraging Cesium for advanced climate simulation and design decision making. Come on up. Thanks, Sherelle.
Thank you. Hi, everyone. By 2100, global temperatures are projected to rise by 4 degrees Celsius. But this isn't just a forecast, it's also a design parameter and a working condition. So I set out to design a tower for that future. And today, I'll walk you through the workflow for that project, Hammock Tower. The tower is a residential project designed to maximize the wind patterns on site for passive cooling. And I'll show you how I used Cesium for Omniverse to bring simulation and site into one design environment. The project is located at 99 Avenue, near Champs-Élysées in Paris. First, I looked at the environmental conditions of the site, wind speed, sun hours, microclimate nuances, and daylight potential. And among all of them, wind showed the greatest potential for passive cooling, and that became the focus of this design response. I used SimScale to simulate wind conditions at a higher resolution. I then processed them in pair review before bringing them into NVIDIA Omniverse. And so what you see here are those wind particle traces from that simulation. With Cesium for Omniverse, I was able to bring Google photorealistic 3D tiles into my design environment, and then combine it with the wind simulation. In typical workflows, architecture lives in one tool, simulation in another, and context is often rebuilt or stitched together from imagery. But for this project, Omniverse was the operating system for connecting my design ecosystem. Simulation tools help me validate design decisions across multiple environmental vectors. But Cesium for Omniverse expands that capability. For this project, it made wind data legible, geolocated, and all within one design environment. Translating data to design, the prevailing southwest wind that you see here that pulses across the site, that drove the architectural strategy. In plan, the building envelope is perforated at the front with the core shifted to the back and then counterbalanced with a structural spine so that the entire front of the tower is open to take advantage of the prevailing wind. And then directly beneath, there are modular pods for short-term stays suspended from it, and they're designed to be lightweight and breathable, like vertically stacked hammocks to capture the wind. Seeing the wind in context helps shape the building as a scaffolding for living units, rather than just one monolithic enclosure. In section, the tower draws wind through gaps between each of the enclosed permanent living units. The units are shaped to compress and then expand the wind to accelerate it via the Venturi effect. And then a central core draws air upward and amplifies airflow through the stack effect. This led to a climate-resilient tower shaped to harness the wind conditions of the site and to maximize passive cooling. So here, overlaid with the simulation lines, this is how I imagine geospatially informed design, where form follows climate. With tools like Cesium for Omniverse, design decisions for climate-resilient architecture can respond in real time and in real context. I'm always excited to meet builders, thinkers, and collaborators, so please feel free to reach out to me on LinkedIn or come say hi during the conference. If you'd like to learn more about this workflow, I'm going to be doing a deeper dive on this at SIGGRAPH in Vancouver this August, so if you'll be there, come find me and we can continue the conversation. Finally, a big thanks to Cesium for the platform to build and for the stage to share. And to the individuals behind these tools and organizations, I'd like to gratefully acknowledge them for helping me do the work that I care about. I'm Sherelle Liu. Thank you all very much.